So let's recall quickly that problem.
So, section 5.1, recursion. So, example, Alice walks on steps on stairways having 10 steps. She can do the moves of length 1, 2, and 4. In how many ways?
This is an arithmetic.
Yes, it is. In how many ways can she make it to the top of the stairways? Very often the way, yes. Okay, thank you. There. Very often when we do recursion, actually, we first warm up with the basic cases. So instead of doing 10 steps, we'll do a more general problem, n steps. That looks surprising. So we kind of prefer general case than a specific one. But general case will give us a chance to progress from one level to the other. So let's number of steps be. So let's an number of ways for n steps and steps, stairways, for the stairways of length n. How much is A1? The 1. How much is A2? If I have 2, then what can she do? She can do 1, 1, or jump 2 immediately, so that's 2. How about A3? 1, 2, 3. She can do what?
Question, why doesn't she start at A0? Because doesn't she just
That's what it is. She's here, yes. She's here at 0. She jumps 1, 2. Here is 3. 1, 2, 3. Yes. So from the level 0, from the ground level, there are 10 steps. So what can she do? Can she do 1, 1, 1? What else? So she can do 1 and then 2, or 2 and then 1, and then.
But she could be able to do
What's it?
She could also start with 4, right? That's the reason why I don't understand why A1 is 1, because she could be starting with 2 steps, or she could be starting with 4 steps.
No. N is the number. How long are the stairways? So this is just short ones. So here it is. So here we have stairways with only 1 step. So here it is. Those are the stairways. Here is the girl. She wants to jump there. In how many ways can she jump up? Just 1. If she's facing from the ground, she's always starting on the ground. She doesn't have a choice where to start. So she goes from the ground to the top. In how many ways can she do it? She can do it 1, 1, or she can jump 2 and be done. What about this one?
Example of 2 stairs, I got you.
Yeah, so this is the next case. So I'm going from case to case. Case 1, case 2, case 3. She can do 1, 1, 1, 2, 2, 1, and that's it. There's no 3 jumps, so A3 is 3. Okay? And now what? Now we want to see what is the general solution, and actually it's very simple to design it if we analyze the last step. So what? If we have a stairs of length n, stairways of length n, so there are n steps on those stairways, then what happens? Let's classify all the trajectories according to the last move, last jump. So what? Last jump equals 1, last jump equals 2, or last jump equals 4. Does this cover all the cases, yes or no? And then what? If her last jump is 1, then how many ways can she finish the story with 1 jump? she can come to the n minus first level however she wants. When we say however she wants, what does that mean? an minus 1. So it says an equals an minus 1. Or, and there is no overlap here, she can come here and make a jump 2. In how many ways can she come to the level n minus 2? Are there any restrictions? No. How she gets there doesn't influence her ability to make that jump. And finally, what plus? n minus 4. So you get to n minus 4 level however you want, and then do the jump of 4. As I said, whenever you design recursion like this, you always want to make it sure that that last step has no influence on the previous history. That's why I can call this an minus 4 unrestricted. And then what is that telling you? All right, so maybe I can now try a4, but unfortunately I cannot. Why not? Because if I want a4, I need someone that's 4 steps below, but that would be a0, which I don't have. So what do I need to do? I have to do a4 on its own, because it has n minus 4. I need first 4 values on my own, and then I'll start running the machinery. So how much is a4? If I have 4 steps, what can I do? 1, 1, 1, 1, if I have no long one. Then if I have length 2 at most, what would that be? That one first, and then what? 2, 1, 1, or what? 1, 2, 1, or 1, 1, 2, or what? 2 2s. Did I forget something on 2s?
1, 4.
No, 1, 3, but with 2s. Now you want 3 steps? 1, 3, or what? No, there's no, just 4, yes. There's no 3 steps move. So how much is this? So 1, 2, 3, 4, 5, 6. So a4 is 6. And what happens now? Now we have machinery. That's how recursion works. Now I can get a10 or any others. So what? How much would be a5 then? Is what? a4 plus a3 plus a1. And that would be, so 4 and 3, where's that? 4 and 3 skip and add 1. So what would that be? 10. How much is a6? So a5 is what we said? 10. How much is a6? You can do it quickly. Add, skip, add. So what would that be? 18. How much is a7? 28, skip 31. And then keep doing it until you get a10, and that will answer the question. This is quite powerful machinery. Design is a little hard. Once you set it up, everything is really nice and works perfectly well. Do we understand the main idea how this works? And I want to show you the same idea in some different settings. So settings change completely, so design has to be different, but the ideas are very similar. Next example, I want to show you one of those rich ones. Is the following example. It is from the text. Okay, Tower of Hanoi, I'll mention that toward the end of the class. That's very simple. Fibonacci number, that's a simple one. Here's a nice question. By the way, they very often ask you this design in some of your computer classes in later education, like automata and so it's interesting to develop this type of skills. So here's the question. By the way, this gives you alternative way to do the counting, even it could be used in chapter 10 in certain situations. The question is, how many 0, 1 strings of a length 10 do not contain consecutive ones? So there are 1,024 strings of length 10. How many of them never have 1 and 1 together? So if we were to do it using combinatorics, that would be a little tricky. There are tons of cases, and it's hard to organize. So example 514, n equals 10, no 1, 1 together. Okay? So here is the recursive formula that we can make. Actually, let's warm up first. I will do general case, and call this number Cn. How much is C1? How many words of length 1 can you make that are legal? Let's call them legal. No one ones is a legal world. Are they both legal?
Yes.
So 2. How about C2? There are 4 of them. One of them is not legal. Who's not legal? 1 is not legal. So there are how many? 3. Do I need C3? I'll see. Maybe I need it, maybe I don't. Let me see. This one?
Yeah.
Oh, here it is. They are 0, 0, 0, 1, 1, 0, 1, 1. So which one's bad? This one, because that's not legal if it has 1, 1. What about here? They're just 0 and 1. None of them is bad. Nothing. Scanner will identify it and say bad word. All right. And here's a very interesting thing. I think that's how I wrote it in the solution. If you look at the manual, or you will see very elaborate analysis of the last place and everything. That's sometimes useful, and I can show you some example where that's useful. This one could be done actually in a much simpler way. So here's what I need. I need Cn plus 1 in terms of Cn minus 1. So I wanted the count of length n plus 1 in terms of the shorter sentences. So here it is. And now, this is the most sensitive part. That's where you do the design. So imagine that I have good word, legal word, so no 1 ones. So I have a good word of length n. And here is the problem. Things will not happen symmetrically. So that's what you need to analyze carefully. So question is, what can I do on the... Sometimes you analyze what you read here and classify according to that. Sometimes you classify according what you will do next. And there are examples when one strategy is better strategy when the other one is better. Let me classify them according to what I'm going to write. So what can I write if I have length n? When I make longer word, what can I write on the next step? Either what? 0 or what? 1. Do you agree? When can I write 0 and stay legal? Always. So that will never. So if this is good, if I add 0, so stays legal always. Do you agree? So how many words will how many legal words will be produced? Whatever the count is here. Count here is what? Cn. So I'll get Cn words that were legal before. I'll glue a 0, so that will give me Cn words. Do you agree? You understand that? If I had 27 words that were good, I will glue 0 and get 27 longer good words. Do you agree with this reasoning? Now what? What if I want to add 1? Will 1 keep everything legal or not? There might be some words that were legal, but will not stay legal. Do you agree? So my question is, how many of them will stay legal? So assume that I'm adding 1, and if I want to stay legal, what must be here? Must be 0, otherwise, so that's it. And then what? So, if it's 0, what about before? It doesn't matter. So how many words do we have now of that type? Cn minus 1. So stays legal only if n word ends with 0. And there are how many? Cn minus 1 of them. And that's it. So what am I getting then? It says Cn plus 1. What?
I think you just mentioned the N word. Never mind.
Only if, what's N word? Oh, there's some, okay. I better not ask further. All right, so Cn plus 1 is what? Cn plus what? Cn minus 1. So words of length n plus 1 are though any word when you glue 0, or word that already was ending with 0, then you are safe to add 1. That's it. I'm done. So now, what? If I have C1 and C2, how much is C3? Just add them up. What do I get? 5. And then C4 is 8, C5 is 13, C6 is 21, C7 is 34, C8 is what? 55, C9 is 89, and C10 is 14, 144. If you look at, as I said, in the solution that I wrote, I wanted to develop a little more machinery. I checked what is the last digit, got some system. At the end, I got the same recursive relation, but gives you a little different machinery. And that shows you power of this process, because once you see how things progress, then you can easily progress through calculation. By the way, everybody knows this recursive relation. That's one of the most famous ones, and historically one of the first one. It's called the Fibonacci connection. And Fibonacci connection, there is an example that I skipped. I'll just mention it toward the end of the class. Fibonacci sequence. This is not classical Fibonacci sequence, because classical Fibonacci sequence starts with 1, 1. And this one starts with what? 2 and 3. So this is a little change, Fibonacci sequence. Yes?
Is there any reason you use C here and A over there?
There is a reason in my notes. I think A and B are some partial sequences, and C was used there. So I wanted to have, that C is the same as C from the notes.
Okay.
So that was the only reason. No other good reasons. What else? Let me revisit one problem. If you remember, one of the harder combinatorial problems that we did was something, it was on the homework, and that was the following. I don't know how many digit numbers, actually I wrote it here. There was a foreign question. How many? Oh, by the way, I will post this one because I showed you the idea of the solution on the board, but I never finished calculation because it was a little messy. But I wrote the full solution, and I had the number. It was the following question we analyzed already earlier in chapter 4. How many 5-digit numbers do not have 5 and 7 together? Or maybe the question was that do have 5 and 7 together, but that's the same thing, you just subtract. So I want to answer the following question. How many 5-digit numbers do not have 5 and 7 together? Okay. So what was the solution we mentioned? It was, we counted, the question in the homework was, do have 5 and 7 together. So if you have 5 and 7 together, then we are saying 5 and 7 can show up on first 2 digits and do the count, or they can show up on second 2 and do count, and then add up the cases, and there is a little messy argument. What's it?
7, 5.
But you double everything, so one of them. So as I said, it's a little, and very sensitive carefully to count. Actually, we will do a much better solution using this idea. Because what? Let's see. Suppose, we can say the following. Let AN, but this will be a little more elaborate. It's not so simple as here, because I have 2 players, 5 and 7, not just 0 and 1. But basically the same idea will work. And here it is. Let AN be the number of n-digit numbers. Number of numbers. Of n-digit numbers that do not end with neither 5 nor 7. And let the Bn be the number of digits that do end I'm sorry, I have to add something. Of legal end digits, what do I call legal? No 5 and 7 together earlier. So no 5, 7 together, but it doesn't end with 5 or 7. Still legal, and it doesn't end with 5 and 7. And Bn is illegal, but ends with 5. And of course, the same thing, Bn is the count for those that are legal, but do end with what? 7. That's the same count, because 5 and 7 have no different properties for this problem. Okay? So what then? Now instead of checking one sequence, I will check two sequences and how they interplay. That's more similar to the solution that I did here. So here it is. Bn again, because they're the same count. But be aware that there are two of them. All right. So here is the word of length n, and I'm building n plus first word. So here's my question. How do I get an plus 1? What am I calling an plus 1? I want a legal word, but a legal word that ends with what? Am I adding 5 or 7 or something else? Look at the name. An is never ending with 5 and 7. It's ending with anything else. So what would that be? 0, 1, 2, 3, 4, and so on. So if I want to build a word, what can I add here? Any number besides 5 and 7. And how many cases do I have then? 8. So could be what? 0, 1, 2, 3, 4, 6, 8, 9. And what could I add it to? Do I need to choose, or it doesn't matter? Like a minute ago, whatever I had before, I can add any of those numbers and keep it a word. Do you agree? How much is whatever? An plus 2bs. Do you agree with me? Why? Because that previous word might be ending with 5, might be ending with 7, that's why 2bns, or end with who knows what. However it ends, I'm okay. How about, yes?
That should be En, right? That big box underneath that.
What is it?
You just wrote N, should that
N is just the length. So length is N. I'm not saying that that's a N, because they are mixed. It might be An, it might be Bn. So I'm just fixing the length. So length is N, this is 1, N plus 1.
Okay.
How about Bn plus 1? I want to, my word, for example, it doesn't matter, 5 or 7 the same way. Let's say I want to write 5 here. Then I write 5. No choice here. I write 5. But when will that keep it legal? When this ends with whatever, just not 7. Do you agree? So how many words do we have there? Either A words or one of the B words, not the other one. So if you want to write 5, then anything but 7. Do you agree? And what else? And that's it. So that means take one word that's not 5 special and put 5, or put the word that is one of the special words, and then just add it up. Here it is. Here's your recursive relation. But uses both A and B, and then the starting values are what? How much is A1? If I make one letter, one digit only, how many of them are legal that do not end with 5 and 7?
I had 9. Oh, no.
Does 0 count?
No.
That's 7.
A1 is, yes, so A1 is 7. How much is B1? 1, because just 5. Ends with 5, and of course there are two B1s. So B1 is the number that ends with 5, that's one of them. And then for 7, another B1, but B1 is 1. How much is A2? Oh, do I need A2?
I got a quick question.
Go ahead.
Shouldn't
No, it's 1.
It can be either ending in 5 or ending.
Yes, but Bn itself is, each of them has its own Bn. That's why here I have 2 Bns. So then what? I don't need A2. Here's machinery. How much is A2?
8 times.
So how much is B2 is easier? 7 and 1. Just previous to 7 and 1 is 8. How much is AN? Add extra BN, which is 9 times 8, 72. So 72 words, they're all together, what? 88 legal words. And out of them, 72 do not end with 5 or 7. 8 of them end with 5, and 8 of them end with 7. And then what do? Can I get A3, A4, and everything? And then what was the question that we had in the homework? What do I need? I need A5 and B5, and I don't want to run it now because you're going to take a break probably. If you continue, you will get that A5 is 67,840. Of course, you can write the program or anything. B5 is 7696. So how do we answer the question then? Because this is just sequence, recursion is ran here. How do we answer the question? Legal words is 67,840 plus 2 times 7696. Why 2 times? Yes, there are 2 BNs, and that's altogether 83232. That's how many legal words are. But that homework question didn't ask you for legal words. It asked you for illegals that do have 5 and 7 together. So that one is 90,000 minus this. And the answer is 6768. So there are 6,768 words. Here is what I would like you to notice here, how powerful this is. You know, you carefully analyze design and how the design changes through stages. Once you notice this, calculation goes very quickly. You know, you can write a program or anything. You're not dependent if numbers are big or small. If they ask for 20-digit numbers, we'll just run a little program and everything is good. And this is also important for programmers because that's what you do when you kind of run some variables through certain set of values and then get progress through calculation. All right, so I hope through these 2 examples you develop some feeling how this works and how powerful it is. And then after the break, we'll just do a few more similar configurations. Yes?
Would it be the same number if it was like, say, 8 and 2? Like you could do any combinations of 2?
Yeah, of course. Yeah, nothing special about 5 and 7.
Yeah.
So the only special one is what?
0.
0. Otherwise, it doesn't matter really which numbers we are analyzing here. As I said, the only part of concentration is here, how do things get inherited from one level to another? Once you have that, everything works. And particularly here, when you see how, what's allowed, what's not, what's keeping your words legal, what not, and then how to do the previous count. For that one might be even better, that simpler problem told you that a little more. How do we progress? On one branch, we had one type of progress. On the other, we had a different one. So symmetry is ruined very often, and that's reflected here. The funny thing is, next week we will learn even how to solve this system, which is similar how we do differential equation, and we can even have formula to just give you immediately explicit formula, but that one involves some square roots, and it's not pleasant to work with. But I can show you that one when we study that machinery next week. Let's take a break. We continue at 2:40.